So this question is asking us to convert the following assembly language instruction to the equivalent machine language. And the first step is to figure out which instruction format this type of instruction uses. So instruction is a setIf less than immediate. And so if we refer to the MIPS reference data sheet, we can scan down this column looking for the setIf less than instruction. And the data that's listed there includes what kind of instruction it is. So a setIf less than immediate is an I-type instruction. And so using the information at the bottom of the sheet, we can see that an I-type instruction is made up of 4 fields. There's the opcode field. This is a 6-bit field. There's 2 5-bit register specifiers, RS and RT, and a 16-bit immediate field. So if we go back to our instruction, the first 6 bits are going to be the opcode. The next 5 bits are going to be RS. The next 5 after that are RT, and the final 16 are the immediate. So we can go ahead and fill in the immediate straight away. So the provided immediate is a hex value F8. Recall that each hexadecimal character encodes 4 bits, and so the F and the 8 specify the last 8 bits of the immediate. Just as in decimal, if we specify a smaller number than we need, it's understood that the values in front of it are zeros. And so the next step is merely to convert these hexadecimal characters into their binary equivalent, which for 0 hex is all zeros in binary, hex F is all ones in binary, and hex 8 is 1 followed by 3 zeros. With that done, we can turn our attention back to the opcode field. And so again, we're doing a setIf less than instruction. So if we refer to our table, again, the setIf less than instruction is going to specify how to encode that opcode. So in this case, it's the letter A in hexadecimal. So again, hex only specifies 4 bits per character, and we have a 6-bit opcode, so that A is going to specify the last 4 bits, and the top 2 bits are going to be understood to be zeros. And so A is the pattern 1010. And now we need to encode the register specifiers. And so we have 2 register specifiers, T1 and A0. We know from writing MIPS that T1 is our destination because it's specified first, and A0 is going to be a source. And so we need to understand the mapping of the destination and source to RS and RT. And so again, the data associated with the setIf less than instruction is going to tell us that, in fact, our destination register is going to specify RT, and the source is going to be put in RS. So our destination register is T1, so that's going to be RT, and RS is going to be A0. In order to figure out the binary encoding of these 2 values, we again return our attention to the MIPS reference data sheet, and in this bottom right corner is information about registers. So again, we can scan this column looking for the registers we care about, and what we'll see is that registers A0 through A3 correspond to registers 4 through 7. So that means A0 is the same as register 4, and T0 through T7 correspond to registers 8 through 15. And so T1 is going to be the same as register 9. So if A0 is the same as register 4 and T1 is the same as register 9, now all we have to do is put the binary encodings of these registers into the instruction. So again, 4 is the value 100, again prepended by zeros. The value 9 is 1001, again prepended by zeros. So now we have a binary encoding for our instruction. If we wanted to do a hexadecimal encoding for the instruction, all we have to do is split up this back into 4-bit hexadecimal characters and come up with the corresponding numbers. So 0010 is the same as 2, 10000 is the same as 8, that's the same, 1001 is 9, and these ones we've already done below. And so the hexadecimal encoding for this set if less than instruction is 288900F8. In this problem, we're going to convert a machine language encoded instruction back into its assembly language equivalent. And the first step to doing this is to convert the hexadecimal representation back into a binary representation, because we're going to want to cut up the bits slightly differently. And so I'm going to write on top here the hexadecimal characters associated with each of these groups of binary digits, and then do the conversion into binary. So 0 is all zeros, 8 is 100, 2 is 0010, 1 is 001, 0 is a bunch of zeros, and 4 is 0100. Once we've done that, we can now cut up the instruction into its pieces. And we don't yet know the type of instruction, but we know that in all instruction formats, this first 6 bits is going to be the opcode. And so we see that the opcode is the value 0. And so what we can do is go to the MIPS reference data sheet, and we can look in this column for the value 0. And what we see is it actually shows up multiple times, that all of these instructions have the opcode 0. And notably, all of them also have, they're all R-type instructions. And so turns out that the opcode 0 is a special case, that all the R-type instructions have the following format, that they have a 6-bit opcode, 3 5-bit register specifiers, those are RS, RT, and RD. There's a 5-bit shift amount, and a 6-bit function code. And so the actual opcode for R-type instructions is specified by 2 fields. It's specified by the conjunction of the opcode field and this function field. And so in order to figure out what instruction this is, we need to identify what the function code is. And I'm going to go ahead and divide my instruction, knowing it's an R-type instruction, into its various components. RS, RT, and RD, again, are all 5-bit register specifiers, and this is the shift amount. And we'll come back to the register specifiers, but the function field we're going to convert back into hex, and that's pretty easy since these top 2 bits here are 0. Our function field is hex 24, the same thing that the bottom 8 bits were. So if we go back here and we scan all of the function fields of the instructions that have opcode 0, what we see is that the AND instruction has the function code of hex 24. So we know our instruction is an AND instruction. And so then we just need to figure out what the registers are associated with it. And because it's an R-type instruction, we also know that there's 3 register specifiers. That there's that RD is going to specify the destination register, and RS and RT are going to be sources. So we need to figure out what those instructions are. So we said RD was going to be the destination, and RS and RT would be the sources. So we can look at each of these register specifiers and convert them back into hex numbers, or I guess decimal numbers. So this is the number 4. This is going to be the number 2. This is also going to be the number 2. So what we need to do is we need to convert these numbers into register specifiers. So we can return to our MIPS data reference, and again, this table down here lists registers, and we can scan this table looking for the numbers 2 and 4. And what we see is that register 2 corresponds to V0, and register 4 corresponds to A0. And so 4 we said corresponds to A0, and 2 corresponds to V0, and that's true for both of these. And so we just need to match them up. So we said RD was the destination, so that's going to be V0. RS is the first source, so that's A0, and RT is the second source, so that's V0. So there is our instruction. And we are done.